Hi everyone, my name is MacLane Wilkison. I am one of the co-founders of NuCypher. NuCypher is the privacy layer of the decentralized web. We believe that privacy is a fundamental human right, and our reason for being as a company is to build the developer tools that allow all of you to build privacy-preserving applications that empower and respect that right. We work on two core technologies, the first of which is our proxy re-encryption network, and which I'll spend most of my time on today. And that is a data privacy and access control layer for decentralized applications. So it gives you a way to store, share, and manage private data on public blockchains and on public file systems like IPFS or the other is more medium and long-term research that we do around lattice cryptography, which we think is one of the more promising areas in cryptography, specifically things like fully homomorphic encryption and lattice-based proofs. But the focus today will be on our decentralized proxy re-encryption network. So this gives you, as developers, a way to provide access controls on top of your DApp. So the obvious question is, like, what's wrong with just traditional public key encryption, or what are the limitations of vanilla asymmetric cryptography? Obviously, things like public key encryption are super well understood. They've been around for a long time. They're very proven. They're relatively easy to use. Simple to sort of reason about. Let's say you have Alice with some message. She wants to confidentially share that message with Bob or Charlie or Dave or Evan. All she has to do is just encrypt that message with the recipient's public key. She sends it across the network. That recipient can decrypt with their private key. It gets a little bit murkier, though, if we start thinking about public key encryption in the context of an application. So almost all of the centralized services we use today are based on basically having everything decrypted server-side. So if we're using Dropbox or Box or Google, all of these great, convenient, super easy-to-use services, almost all of them have some multi-user component, right? So if Alice uploads some data, even if she encrypts it client-side, if that application needs to share that data with anyone else, they have to have some way to decrypt that data on the server and share it again onto the Bob or Charlie. And maybe that's okay, maybe we trust Google, we trust Dropbox. I guess that's debatable. But at the end of the day, even if we trust those service providers, having everything decrypted server-side is obviously a huge honeypot for black hat hackers or malicious actors. People like those guys that are trying to break into decentralized service providers. And then if we take the next step to this decentralized world that we're all building together, having things decrypted server-side are a complete non-starter. Because server is not sitting in Google's data center, it's not sitting in Facebook's data center, it's maybe an IPFS node that's controlled by a malicious regime, or it's a node that's sitting in some random person's basement. The idea of having sensitive data in the clear on some node or on some server in a decentralized application is just a complete non-starter. So we need some way to sort of close this loop and have everything encrypted from the data owner side until it reaches the ultimate intended recipients. And that's what proxy re-encryption does. So with proxy re-encryption, we can, or Alice, some data owner, can encrypt her data client-side, she can upload it to storage, and then some untrusted proxy can basically delegate or re-encrypt access, or delegate access or re-encrypt the data from being encrypted under Alice's key into being encrypted under Bob or Charlie or Dave or Evan's key. And the magic part about proxy re-encryption is that this transformation or re-encryption happens without ever decrypting in the middle. So you get ciphertext in, ciphertext out. The proxy can never see the plaintext data, the storage layer can never see the plaintext data. Only Alice and whoever she explicitly shares the data with. We have a little video to explain that a little bit more visually. So here is Alice. She has some sensitive data on her local machine. She encrypts that data before uploading it and sending it off to storage. This could be sent to IPFS or Swarm or S3, it doesn't matter. At this point, the data is encrypted under Alice's key. She's the only one who can decrypt it. Let's say Bob comes along and tries to access that data. So he has his own key pair, he tries to use that key pair to decrypt the data. That's going to fail. But then later on, Alice decides, okay, Bob should actually have access to this data. So what she can do with proxy re-encryption is she can create something called a re-encryption key. And a re-encryption key has two inputs. The first is Alice's private key, and the second is Bob's public key. But once you've created a re-encryption key, there's no way to get those two pieces back out, so there's no way for anyone to get the private key of Alice back out. She can send this re-encryption key to a node in the NuCypher network, and that node, or in our case, multiple nodes, will use that re-encryption key to rekey or re-encrypt or transform the data. Once that re-encryption has happened, Bob will be able to decrypt. And the incentive for a NuCypher node is obviously they're compensated for this service. So they'll accept re-encryption key fragments from Alice, and they'll perform re-encryption for Bob. Once that re-encryption has happened, Bob can use his own key pair to then decrypt the data, and he will have access. We've actually taken this a step further. So instead of vanilla proxy re-encryption, where you have one re-encryption key and one proxy, at NuCypher, we've actually created a threshold split key re-encryption scheme, which splits that re-encryption key up into multiple fragments. In this example, 5. Sends those fragments out to different nodes in the NuCypher network, and then the data owner can specify some threshold number, in this example 3, of those re-encryption key fragments that need to come together in order to properly re-encrypt. So what this does is it spreads the trust across multiple nodes in the network. So you have a lot of benefits like redundancy, so if a node goes offline, the re-encryption will still work. If one of the nodes becomes malicious for some reason, it's fine, the system it's trustless. So basically the NuCypher network consists of a bunch of these nodes scattered all over the world that are taking re-encryption keys from data owners, performing this re-encryption on demand and giving access to valid recipients. And if you want to be one of those nodes, and the reason why you want to do that is that nodes are paid by users for this service, you have to stake the NuCypher token. So the NuCypher token is used as a type of bond or collateral that allows you to run a node, and we primarily use it to coordinate our network. So if you're staking, let's say 5% of the NuCypher tokens, you'll probabilistically get 5% of the work, and if you do that work correctly, you'll probabilistically get 5% of the rewards. So it compensates honest nodes, and then it's also used to punish malicious nodes. So if you stake and you say I'm going to run a node for 6 months, and then you just go offline, you disappear, you don't accept re-encryption keys, or worse, you provide false or fake re-encryptions, your stake will get slashed and you'll have this economic penalty. One of the things that we were actually very conscious about in designing our system is that we do not use our token as a kind of payment. So nodes will actually get paid in ETH to start by users of the network, potentially in the future other payment tokens or other stable coins, and they also get additional compensation via inflation of the NuCypher token. But we didn't want to require a DApp developer or an end user of an application to go and acquire NuCypher tokens to use the network. That just introduces a bunch of friction, and we wanted to make it as easy as possible for people to adopt and use the system. So this is just a sample of a few of the users that are building on top of NuCypher. As you can see, a lot of healthcare projects, projects like MediBlock, which is a Korean project, is building a patient-controlled medical record system. We're also the access control layer for a lot of the new decentralized databases, like BUIDL, Fluence, and Wolk. Origin is another interesting user, so there is a sharing economy protocol, and they're using it for sort of generalized secrets management. So let's say you built a decentralized Airbnb on top of Origin. You obviously don't want your house address to be totally public. You only want to reveal that, say, when someone's made a booking. We also work with a lot of the data marketplaces and data exchanges like Datum or Ocean Protocol. We're aggregating a bunch of different kinds of data, encrypting it, and then trying to monetize it by selling it or renting it out to researchers or advertisers in exchange for payment. So you can have like conditional encryption where you have some encrypted data and you only want to grant someone access if they pay like 5 ETH to your address, for example. So right now we are running this network sort of in a private testnet with a few of our early staking partners. And the next several weeks to a month, month and a half-ish, hopefully, we will have a public testnet available, including a testnet faucet where you can hit that to grab some NuCypher tokens to stake and run a testnet node. And that public testnet will be more or less a feature-complete testnet that will look very close to what will be on mainnet. So it'll be fully implemented, have all the functionality in terms of conditional access and staking and payments and all of that. So Just to wrap up, I'll touch a little bit briefly on the research we're doing around FHE and lattice cryptography. And for those of you who aren't familiar with fully homomorphic encryption, FHE is this idea that you can perform arbitrary computations on encrypted data. So in exactly or a similar way that you can take some plain text data, perform some processing or computation on it and get a result, FHE says that you can have encrypted data, perform some process or computation on top of it while it's still encrypted and get an encrypted result. So this has a lot of interesting applications. For example, theoretically, you could have like a fully encrypted genomics database where you have many different patients contributing their genomics data. You allow outside researchers to perform some kind of research or processing or machine learning algorithms on top of that encrypted data and get the results for their research, but without compromising the personal health information of all those patients. Our interest in lattice cryptography and FHE obviously is more focused around things in the blockchain and cryptocurrency space. So we're looking at potentially how to use it for things like fully homomorphic smart contracts, private payments, things like that. A lot of the research we do is private for now, but we do release some of what we do. Probably the most interesting is our new FHE library, which is a GPU implementation of homomorphic encryption that is about 100x faster than some of the previous libraries. So we have about 7,000 gate operations per second right now, which actually is fast enough for pretty much most smart contracts, given that they're not performance sensitive. And actually, we used this library about 2 months ago or so to execute the first ever fully homomorphic smart contract at ETH Berlin. That's also open source. That's on our GitHub. You can check it out, as well as the smart contract that we did at ETH Berlin. So that's most of what I have. We'll be doing a workshop tomorrow morning, first thing. So we'll be playing around with our testnet. I'll show you how to spin up a node, join the network, perform re-encryptions on the node side, and then on the user side, how to build a sample healthcare application. If you can't make that for some reason, we're also doing a meetup with QuantStamp at Hash Lounge tomorrow night. So hopefully I'll see you at either of those places. And obviously I'll be around the rest of the day and tomorrow and happy to chat with you guys offline. If you want more information, our website, technical white paper, virtually all of the work we do is open source and public, even our development discussions with our team. So if you want to engage with us on a technical level, talk about staking, write nodes, or building applications, please do join our Discord, and we're very eager to connect with you there. Do I have time for a couple questions? Cool.
네, 혹시 질문 있으시면 손들을 표시해 주시면 마이크를 가져다 드리겠습니다.
All right. Thank you, guys.